All right, buckle up, everybody, because today we're taking a deep dive into something pretty wild.
Yeah, this is going to be a fun one.
A theory that's shaking up some of the biggest ideas in physics. We're talking black holes, gravity, even the origin of the universe, the whole shebang.
Exactly.
Yeah.
And what's really fascinating is the source material we're looking at.
Right.
It's not just some fringe idea. It's based on a book called Gravity and Creation.
Okay.
And it lays out this whole new framework they're calling Grand Fibonacci.
Grand Fibonacci. Okay, I'm intrigued already.
And get this, it directly challenges some of the most famous work of, Stephen Hawking.
Whoa, hold on. So we're talking about potentially rewriting textbooks here.
That's the idea.
What's the core of this challenge? What are they saying that's so different?
It all starts with black holes.
Okay.
See, Hawking's work, which was based on Einstein's theory of general relativity,
Right.
it leads to this idea of singularities.
Yeah, singularities, those points of infinite density.
Exactly, where gravity is so strong that everything just collapses in on itself.
Right. To a point of, well, basically nothing, right?
Right, basically oblivion. But Grand Fibonacci says, hold on, not so fast.
Whoa, no singularities. That's a pretty big claim right there.
It is a huge departure from conventional thinking.
So what's their alternative if everything's not collapsing into these points of nothingness? What's happening?
They propose this concept called negative vacuum synergy.
Oh, okay.
Imagine instead of everything being pulled inwards into a singularity,
Yeah.
there's actually this kind of pressure pushing outwards, preventing that total collapse of matter.
Hold on. So it's like the universe has built-in safety brakes. Like there's a limit to how much things can crunch down.
That's a good way to think about it.
Okay, so in this model, black holes, aren't these all-consuming monsters just crushing everything into oblivion?
Not exactly.
Hmm.
They become more like, dynamic systems with finite interiors, not those points of infinite density, where matter and energy are constantly interacting in this, push and pull between gravity and this negative vacuum synergy.
Yeah. So instead of a one-way ticket to oblivion, black holes are more like cosmic pressure cookers.
That's a good analogy.
I mean, it completely changes how we visualize these things, right?
It does. It really challenges that classic image of black holes we all have.
And this isn't just a thought experiment, right? They actually have some math to back this up.
Oh, yeah. The paper gets into the nitty-gritty.
Okay.
It uses all these equations to model these interactions, these forces at play.
What kind of forces are we talking about?
They describe these subtle magnetic fields, or SMFs.
Okay, I said.
And these areas they call relative vacuums, RVS.
RVS. All right, keep going.
And they say these things are constantly interacting to create this pushback effect.
So just to make sure I'm following, these SMFs and RVS are like opposing forces within the black hole, and they're preventing the singularity from actually forming.
Exactly. It's this constant dance between them.
Okay, I'm starting to get it.
Yeah.
So what does all this mean for Hawking's idea about black hole evaporation?
That's where things get even more interesting.
I'm all ears.
You see, Hawking theorized that black holes slowly evaporate over time.
Right, they kind of leak radiation and eventually disappear completely.
Exactly. But in the Grand Fibonacci model,
Yeah.
with this negative vacuum synergy pushing back, black holes might not evaporate entirely.
Whoa, so they're saying black holes might not actually be these cosmic death traps we thought they were?
That's what this theory suggests.
Right.
It's a totally different picture of how black holes might behave, way more dynamic and long-lived than we ever imagined.
I'm officially mind blown. So if we're rethinking black holes, what other big ideas does this Grand Fibonacci thing shake up?
Well, let's talk about the Big Bang, shall we?
Oh, you're not about to tell me the Big Bang didn't bang, are you?
Not exactly. More like we might need to rethink what that bang actually looked like.
Okay, I'm very curious. Let's hear it.
So Hawking, he believed the universe started with a singularity.
Right, that infinitely dense point that explodes outwards and boom, the universe is born.
Exactly. But Grand Fibonacci offers a different picture. They're saying the early universe wasn't a point of infinite density, but a state of, get ready for this, infinite fractal expansions.
Okay, you officially lost me, fractals. Like those trippy patterns you see in nature.
Exactly. Like snowflakes, where you see the same basic pattern repeated at different scales.
Right, I get it.
So Grand Fibonacci suggests the universe's earliest state was something similar. An interconnected web of energy expanding outwards in this, fractal pattern.
So instead of exploding from a single point, the universe is more like unfolding outwards from this intricate, interconnected state.
That's a great way to put it. It's a completely different way to think about the universe's beginnings.
Okay, my mind is officially bending.
And this fractal nature, According to the paper, it's tied directly to those SMFs and RVS we were talking about before.
You mean those forces at play inside black holes?
Exactly. The same forces that govern black holes might also be responsible for the universe's initial expansion.
So this grand Fibonacci theory sounds like it has the potential to rewrite everything we thought we knew about the universe.
It's definitely a game changer, at least in terms of how we think about things.
My brain needs a minute to process all of this. I think our listeners probably do too. This is some seriously mind-blowing stuff. We're just scratching the surface of this grand Fibonacci rabbit hole, and trust me, there's a lot more to explore.
Oh yeah, we're just getting started.
So let's take a moment to absorb all of this, and then we'll come back and dive even deeper.
Sounds good. I'm ready for round 2.
Me too.
All right, let's do it.
All right, I think I've managed to reboot my brain after that last segment.
Good, good. Because we're just getting started with grand Fibonacci. Remember this theory? It's not just about black holes. It wants to be a theory of everything.
Yeah, a framework to explain, well, everything.
All the fundamental forces, all the big mysteries of the universe, the whole 9 yards.
Okay, that's a tall order.
Yeah.
So what are some of the biggest puzzles it tries to solve? Besides, rethinking black holes.
Well, let's take dark matter, for example.
Yeah. Okay, dark matter.
The invisible stuff that supposedly makes up, 80% of the universe's mass.
Something like that. Astronomers have observed that galaxies, they behave as if there's way more mass there than we can actually see.
Right. It's like this cosmic glue holding everything together.
Exactly. And the standard model of physics, it tries to explain this by saying, well, there must be these new undiscovered particles out there.
Okay, so dark matter is made of these, phantom particles we haven't found yet.
That's the current thinking. But Grand Fibonacci says, wait a minute, what if we don't need any new particles?
Really? So no missing particles, just missing explanations.
Precisely. They propose that dark matter, it's actually a large-scale effect of, you guessed it, those SMFs and RVS interactions.
Oh, right. Those subtle magnetic fields and relative vacuums, those things are everywhere.
Everywhere. And they're constantly pushing and pulling, creating this dynamic energy field throughout the universe.
So instead of invisible particles, it's these invisible forces creating those gravitational effects that we attribute to dark matter. That's the idea. The paper suggests these interactions, happening at these huge galactic scales.
Yeah.
They can actually mimic the gravitational pull we attribute to dark matter without needing any exotic new particles.
Okay, that's a pretty neat solution, I have to admit. But what about dark energy?
Yes, dark energy.
That's the force that's making the universe's expansion accelerate.
Yeah, got it. And again, Grand Fibonacci, it offers a unique perspective. Remember those fractal expansions we discussed earlier?
Yeah, the idea that the universe is unfolding in these repeating patterns like a cosmic snowflake.
Exactly.
Oh.
Well, they suggest that these fractal expansions themselves,
Yeah.
they're actually driving that accelerated expansion. It's like the fabric of space-time itself. It's programmed to stretch and grow.
So instead of some mysterious dark energy pushing everything apart, it's more like the geometry of the universe itself causing the acceleration.
That's their argument. They're saying the universe is constantly unfolding, driven by these underlying SMF and RVS interactions. And that creates the illusion of dark energy.
Okay, my head is spinning. This is a lot to take in. So we've got black holes that might not be as destructive as we thought.
Right.
A big bang that might have been more of a cosmic unfolding.
Yeah.
And now, dark matter and dark energy, explained by these fundamental push-pull forces. Anything else I should know about?
Oh, there's more. Don't forget about gravity.
Right. Grand Fibonacci, they have a whole different take on gravity too, don't they?
They do. They're saying that gravity, well, it's not even a fundamental force.
Whoa, wait, what? So gravity's not baked into the universe from the get-go?
Not according to them. They say that instead of gravity being this inherent property of matter.
Like, how Einstein described it, the warping of space-time?
Exactly.
Yeah.
They propose that gravity, it actually emerges from the interplay of, you guessed it, those SMFs and RVS.
Those two again, huh? They really are the stars of the show.
It's like gravity is a side effect of these subtle interactions happening constantly throughout the universe.
Okay, so gravity is more like an emergent property of these forces, not a fundamental force itself.
That's their argument.
Wow, that's a pretty radical concept. If that's true, what does it even mean for, our understanding of how the universe works?
Well, for starters, it could totally change how we think about the structure of the universe.
Yeah.
How galaxies form and evolve. If gravity isn't this fundamental force, but this emergent one, then a lot of our assumptions about the universe need to be re-examined.
Okay, this is all pretty mind-blowing, but is there actually any way to test any of this? It seems very theoretical.
That's the thing with any new scientific theory. It has to be testable, right?
Right.
And the paper does suggest some ways we might be able to actually observe evidence for this model. But it'll take some, serious advancements in our technology and observational capabilities.
Okay, so what would we need to look for?
Well, if Grant Fibonacci is right, we should be able to detect signs of this negative vacuum synergy around black holes.
Hmm, and how would we do that?
It might show up as like subtle variations in the gravitational pull around a black hole,
Okay.
or even the radiation coming from these objects.
Yeah. So astronomers would have to look for things that don't quite fit with what traditional black hole physics would predict.
Exactly. Deviations from the norm. And when it comes to the Big Bang,
Yeah.
cosmologists, they could look for specific patterns in the cosmic microwave background radiation.
The afterglow of the Big Bang, right?
Exactly. Patterns that would support this idea of fractal expansions.
Okay, so it's not all just wild speculation. There are ways to potentially verify these claims.
Absolutely. The scientific method,
Yeah.
it demands that any theory, no matter how elegant or revolutionary,
Yeah.
it's got to stand up to rigorous testing and observation.
Okay, I'm convinced. This grand Fibonacci theory, it's seriously compelling. But I have a feeling we haven't even gotten to the most controversial part yet, have we?
You're right. We've talked about how this theory challenges our understanding of black holes, the Big Bang, dark matter, dark energy, even gravity itself.
Huh.
But the paper goes a step further. It makes a very bold claim about Stephen Hawking himself.
Okay, now you've really got me hooked. Let's hear it. What does Grand Fibonacci have to say about Hawking's work? Okay, so we've explored how Grand Fibonacci reimagines black holes, the Big Bang, even gravity itself. What's this bold claim about Stephen Hawking's work?
Well, the paper uses a pretty strong word to describe it.
Oh,
It argues that Hawking's framework, especially when it comes to singularities and gravity,
yeah.
it's superseded by Grand Fibonacci.
Superseded. That's a pretty strong statement, isn't it?
It is. It's basically saying, thanks for laying the groundwork, Hawking, but we've got a better model now.
Yeah, I mean, that's not going to go over well with everyone, is it?
Probably not.
And
But remember, this paper isn't just proposing some minor tweaks to existing theories.
right, it's a whole new way of looking at things.
Exactly. It's suggesting a fundamental shift in our understanding of the universe.
Yeah.
And that means, well, revisiting even most well-established ideas.
So if we really try to see the universe through this grand Fibonacci lens, what does that even look like? How does our picture of reality change?
Well, first and foremost, it's a universe without singularities.
Okay, no points of infinite density, no breakdown of physics.
Right. Instead, you have this dynamic interplay of SMFs and RVS.
Right, those subtle magnetic fields and relative vacuum.
Exactly, governing everything, from how black holes behave to the expansion of the universe.
It's almost like the universe has these built-in checks and balances to keep things from going completely haywire.
That's a good way to put it.
Uh-huh.
And it has some pretty profound implications.
Like what?
Well, for one thing, it suggests that black holes, even though they're incredibly powerful objects,
Yeah.
they're not those inescapable cosmic vacuum cleaners we once thought they were.
Because of that negative vacuum synergy pushing back against gravity. Right?
Exactly. It prevents matter from totally collapsing into a singularity. And that means Hawking's idea that black holes eventually evaporate completely.
Hmm.
Well, that might need to be reconsidered too.
So black holes might not just disappear, they might actually stick around.
Potentially, yeah. With this push-pull dynamic, they could reach a state of equilibrium and remain stable for, incredibly long periods.
Wow, so instead of just being points of destruction, black holes are more like, I don't know, cosmic engines, constantly churning and evolving.
That's a great analogy.
Yeah.
And then, if we extend this idea to the Big Bang,
Yeah, the very beginning of everything.
right, well, it challenges that traditional picture that Hawking painted.
Of everything exploding out from a single point.
Exactly. Instead, Grand Fibonacci suggests this more gradual unfolding, driven by those fractal expansions.
So to clarify, it's not that the universe exploded outwards from nothing.
No.
It's more like it was always there in this really compact, interconnected state, and then it started to expand and unfold based on these repeating patterns.
You got it. It's a very different picture.
Yeah.
But the paper argues that it fits the data just as well, if not better, than the traditional Big Bang model.
This is seriously mind-blowing stuff. It feels like we're on the verge of a whole new understanding of the universe.
I think that's the most exciting part of theoretical physics.
It is.
It forces us to challenge our assumptions, to explore new possibilities, even if they sound radical at first.
But let's be real here for a second.
Oh, okay.
This grand Fibonacci theory, it's still pretty controversial, right? I mean, not everyone in the scientific community is going to just accept this.
Of course not. That's how science works,
Yeah.
right? New ideas, they're met with skepticism, debate, rigorous testing.
And that's a good thing.
Absolutely. It's how we refine our understanding, how we separate the truly groundbreaking ideas from the ones that, well, just don't hold up.
So what needs to happen next? How do we figure out if this theory is right or wrong?
We need more evidence, more observations.
Like what?
Remember those tests we discussed earlier?
Mhm.
Astronomers, they need to keep looking for signs of this negative vacuum synergy around black holes.
Right. Those deviations from what we'd normally expect?
Exactly.
Yeah.
And cosmologists, they need to keep studying the cosmic microwave background radiation, looking for those patterns that might point to fractal expansions.
And if those observations, if they don't match up with what the theory predicts,
Well, then it might be time to reevaluate.
back to the drawing board.
Maybe. But even if Grand Fibonacci turns out to be, not the ultimate answer,
Yeah,
it's already sparked this incredible conversation. It's pushed the boundaries of our imagination.
I completely agree. So as we wrap up this deep dive, I think the biggest takeaway for our listeners is this. The universe is a much stranger and more wondrous place than we often give it credit for.
Absolutely. And even our most cherished scientific ideas,
Yeah.
they're always subject to revision, refinement, rethinking.
And who knows, maybe someday we'll look back at Grand Fibonacci and see
Yeah.
it as one of those moments that completely changed our view of the cosmos.
It's definitely possible. Until then, the journey of discovery continues.
Well said. So, to all our listeners out there, keep looking up, keep questioning, and keep your minds open to the infinite possibilities that the universe holds. And until next time, happy exploring.